Prompt engineering sounds complicated, but every technique in this field started from the same place. Just asking the model to do something. No examples, no tricks, no elaborate frameworks. That's zero-shot prompting, and it's the foundation everything else is built on. But here's the thing, most people get it wrong, and understanding why it fails is the entire reason this video exists. Let's start simple. Zero-shot prompting. This is the just ask it technique. You give the model a direct instruction with zero examples, and it draws entirely on its pre-training knowledge to respond. Something like classify this text as positive, negative, or neutral. No demonstrations, no hand-holding, just a clear task and a prayer. And honestly, for simple stuff, it works shockingly well. But here's where it gets complicated. The difference between a good zero-shot prompt and a bad one is enormous. Summarize this into 3 key points. Consistently, destroys make it shorter. Why? Because the first prompt removes every ounce of interpretive ambiguity. The model knows exactly what you want, how many points, and what format to deliver them in. The second prompt is vague, and vague inputs produce vague outputs every single time. Best practices are deceptively straightforward. Put your instruction at the start of the prompt, not buried in the middle. Use clear delimiters like triple quotes or hash symbols to separate your instruction from your input data. Keep your language simple. You're given directions, not writing poetry. Now here's the ceiling nobody talks about. Zero shot works great on well-defined single-step tasks. Classification, translation, basic summarization. But the moment you need multi-step reasoning, it starts falling apart. Ask it to solve a complex logic problem with zero guidance, and you'll get confident nonsense. There's also a genuine scientific debate happening right now about whether zero-shot capabilities are truly emergent abilities that appear as models get bigger, or whether these capabilities always existed and just become visible when you prompt correctly. Researchers still can't agree, but that failure ceiling, that exact moment where just asking stops working, is what drove the creation of every single technique that follows. And the first solution researchers found was embarrassingly obvious. Few-shot prompting. Zero-shot prompting is powerful, but it has a glaring weakness. You're asking the model to figure out what you want based on instructions alone. Few-shot prompting fixes that by doing something deceptively simple. Instead of describing the task, you show the model what correct outputs look like. Here's a classic example. You type Jane Smith to Smith, Jane and Robert Johnson to Johnson, Robert into your prompt. Then ask the model to parse a new name. No explanation needed. The model extracts the pattern from your examples and applies it perfectly. You didn't teach it anything new. You activated a pattern matching process it already had buried in its training data. And this is where it gets really interesting. Few-shot prompting is absurdly effective for format enforcement. Let's say you need the model to return structured JSON. You could write 3 paragraphs explaining exactly how you want the data formatted, every field name, every nesting level, every data type. Or you could just paste 2 example JSON outputs into the prompt. The examples outperform the verbal instructions almost every single time. The model sees the structure, internalizes it, and replicates it with near perfect consistency. The number of examples you need scales with how hard the task is. Simple pattern matching? 1 or 2 shots will do. Complex reasoning tasks with nuanced rules? You might need 5 to 10 demonstrations before the model reliably gets it right. And here's something most people don't realize. The order you place those examples in your prompt actually changes the output. Swap example 1 and example 3 and you can get a measurably different result. Few-shot prompting isn't just mechanical copy-paste. Shot selection is a genuine skill, but here's the ceiling. Few-shot prompting learns surface patterns. It's incredible at replicating formats and extracting rules from examples, but the moment you throw a multi-step arithmetic problem at it, everything falls apart. The model sees the pattern of question, then answer, but never shows its work. And invisible reasoning is unreliable reasoning, which is exactly why the next technique exists. Chain of thought prompting. Here's the thing about large language models that most people get completely wrong. They assume chain of thought prompting makes the model smarter. It doesn't. The reasoning capability was always there, buried inside the weights, invisible. Chain of thought doesn't upgrade the model. It forces the model to show its work. And that single shift changed everything about how we use AI. Before chain of thought, prompting was basically ask a question, get an answer. The model would jump straight from problem to conclusion with zero transparency into how it got there. Chain of thought flips that entirely. Instead of asking for an answer, you instruct the model to reason through the problem step by step before arriving at a conclusion. You make the thinking visible, and the results are staggering. Let me give you the numbers. On the GSM-8K math benchmark, a 540 billion parameter model using just 8 chain of thought examples achieved state-of-the-art results. It surpassed fine-tuned GPT-3 models that had dedicated verifiers built on top of them. Accuracy Accuracy improvements of up to 41% were documented, not 4%, 41, from a technique that in its simplest form requires adding 5 words to your prompt. That's the zero-shot variant. You literally just append. Let's think step by step to your prompt, and the model starts decomposing problems into intermediate reasoning stages. It sounds almost stupidly simple, but it works because chain of thought reasoning appears to be an emergent capability, something that unlocks once models hit a certain scale. Smaller models don't benefit much. Large models suddenly start reasoning like they've been doing it all along, because they have. You just couldn't see it. The few-shot variant is more robust. Instead of hoping the model figures out what step-by-step means, you provide complete worked examples with full reasoning chains. The model sees how you want problems broken down, internalizes that structure, and applies it to the real problem. Think of it like showing someone your scratch work on a math test before handing them a new equation. But beyond raw accuracy, there's a benefit that matters even more in high-stakes applications: transparency. When the model shows its reasoning chain, you can catch hallucinations mid-process. You can see exactly where the logic breaks down before a wrong intermediate step corrupts the final answer. In medicine, law, finance, anywhere the stakes are real, that visibility is enormous. Now, chain of thought isn't universally useful. Simple, factual lookups don't benefit. Basic classification tasks don't need intermediate reasoning, and generating all those extra reasoning tokens costs additional computation and money. You're paying for every step the model writes out, but for anything requiring genuine reasoning, this is the technique that proved prompting isn't just about asking better questions. It's about unlocking capabilities the model already had. If you think making one model reason step by step is impressive, wait until you see what happens when you make it reason through the same problem multiple times and pick the best answer. Self-consistency prompting. Think of it this way. You ask one person a tricky math question and they might get it wrong. But if you ask 40 people the same question independently and 35 of them arrive at the same answer through completely different methods, you trust that answer. That's self-consistency prompting. It's the wisdom of crowds applied to AI reasoning. Here's the core insight. Complex problems almost always have multiple valid reasoning paths that lead to the same correct answer. Chain of thought prompting picks one path and commits to it. Self-consistency says that's reckless. Instead of trusting a single chain of reasoning, you sample many different chains and let them vote. The implementation is surprisingly straightforward. You take the exact same few-shot chain of thought prompt and run it multiple times with varied sampling, usually by adjusting the temperature parameter so the model explores different reasoning trajectories each time. Then you extract the final answer from every single run and pick whichever answer appears most frequently. That's it. Majority rules. And this directly attacks chain of thought's biggest remaining weakness. A single reasoning chain can go wrong at any intermediate step, and once it does, everything downstream is corrupted. One bad calculation in step 3 means step 4, 5, and 6 are all wrong too. But when you have multiple independent paths working the same problem, individual errors become statistically unlikely to dominate the vote. One chain makes a mistake in step 3, doesn't matter. The other 15 chains got it right. The results back this up. On GSM 8K, one of the hardest arithmetic benchmarks, self-consistency boosted accuracy by nearly 18% over single path chain of thought. Across other reasoning benchmarks, the gains range from around 4% to 12%. That's not marginal. That's a meaningful leap in reliability across the board. But here's where it gets interesting. Not all reasoning chains are equally trustworthy. Complexity-based prompting extends self-consistency by preferentially weighting the most complex chains, the ones with more intermediate steps, and more thorough reasoning. The intuition is simple. A chain that takes 12 careful steps to reach an answer is a more reliable witness than one that jumps to a conclusion in 3 steps. Thorough reasoning beats heuristic shortcuts. This approach yields an additional average gain of 5.3% across benchmarks, reaching 18% on complex tasks like MathQA. Now, the honest trade-off. You're running the model multiple times per query. Computational cost scales linearly with the number of sample paths. If you sample 20 reasoning chains, you're paying for 20 runs. For simple questions, that's overkill. For high-stakes complex reasoning where accuracy actually matters, it's worth every token. But if you think running the same model multiple times is clever, wait until you see what happens when you let the model argue with itself. Step back prompting. This one is almost too simple to work, but it does, and the results are kind of ridiculous. Here's the idea. Before you ask a model to solve a specific problem with specific numbers and specific details, you first tell it to zoom out. Identify the general principle. Figure out what concept governs this type of problem. Then, and only then, apply that concept to the actual question. Think about it like this. Say you have a physics problem involving solving a specific object moving at a specific velocity. Instead of throwing the numbers at the model immediately, you first ask what physics principles are relevant here. The model identifies Newton's laws, conservation of energy, whatever applies. Then you feed it the actual problem. Now it's building on conceptual bedrock instead of fumbling through numbers, hoping to land on the right formula. It sounds like advice your college professor would give you. Understand the theory before you do the math. And that's exactly why it works. Language models are trained on enormous bodies of conceptual and theoretical text, textbooks, academic papers, encyclopedias, technical documentation. Step-back prompting taps directly into the conceptual layer before asking the model to reach into specific facts and calculations. It's basically forcing the model to activate its strongest knowledge base first, then channel that understanding into the concrete problem. 2 stages: abstraction, then application. And the benchmarks back this up in a big way. MMLU physics scores improved by 7%, chemistry improved by 11%. But here's the standout number: time QA, a temporal reasoning benchmark, improved by 27%. That's not a marginal gain. That's a completely different tier of performance from a technique that essentially just says, think about the big picture first. Multi-hop reasoning on MuSQA also saw a 7% improvement, which matters because multi-hop questions are exactly where models tend to lose the thread. Now, while we're on the topic of learning from contrast, there's a complementary technique worth mentioning here: contrastive chain of thought. Standard chain of thought gives the model examples of correct reasoning. Contrastive chain of thought adds examples of incorrect reasoning alongside them. You're literally showing the model what mistakes look like, not just what success looks like. It teaches the model to recognize and avoid common errors, providing a richer learning signal without any additional computational cost. Same overhead, better results. Both techniques share this core philosophy of learning through opposition and contrast rather than purely positive demonstration. But if step-back prompting is about zooming out to see the big picture, the next technique is about doing the exact opposite, breaking problems into the smallest possible pieces. Tree of thoughts. Everything we've covered so far follows one path. You think step by step, you get an answer, you move on. Tree of thoughts throws that entire approach out the window. This isn't a prompting trick. This is a reasoning architecture. And the performance gap it creates is honestly hard to believe. Here's the concept. Instead of following a single linear chain of reasoning, Tree of Thoughts treats problem solving like a branching tree search. Think about how a chess engine works. It doesn't just consider one move. It generates multiple possible moves, evaluates which ones look promising, pursues the best branches, and prunes the dead ends. GPS routing does the same thing. Tree of Thoughts applies that exact logic to language model reasoning. At every decision point, multiple candidate reasoning steps are generated simultaneously. Each candidate gets evaluated for how likely it is to lead to a correct solution. The most productive branches get explored further. The clearly unproductive ones get cut. The model isn't locked into a single path anymore. It can look ahead, backtrack, and course correct. Making this work requires 3 components. First, a thought generator that produces candidate next steps at each branching point. Second, an evaluator that scores each candidate's likelihood of actually reaching a solution. Third, a search algorithm, either breadth first or depth first, that navigates the tree structure and decides which branches to explore next. These 3 pieces working together transform a language model from a linear thinker into something closer to a strategic planner. Now here's the number that sells this entire technique. The game of 24 is a mathematical puzzle where you combine 4 numbers using basic operations to reach exactly 24. It requires strategic thinking because early choices constrain everything that follows. Standard chain of thought prompting with GPT-4 solved this puzzle 4% of the time. Tree of Thoughts with GPT-4 solved it 74% of the time. That's not a marginal improvement. That's the difference between a technique that functionally doesn't work and one that works most of the time. That gap exists because certain problems demand look ahead and backtracking. Creative writing that needs structural coherence across an entire piece. Strategic planning where one bad early decision ruins everything downstream. Complex mathematics where you need to explore multiple approaches before committing. These are exactly the problems where a single reasoning chain falls apart, and researchers have pushed this even further. Graph of Thoughts removes the parent-child restriction of trees entirely. Any thought can connect to any other thought, meaning insights from one reasoning branch can directly inform a completely separate branch. Multimodal extensions incorporate visual information alongside text, expanding the framework beyond pure language. The honest caveat is cost. Exploring multiple branches multiplies token usage significantly. You're generating and evaluating far more content than a single chain of thought pass, but aggressive pruning of clearly unproductive paths keeps things manageable. And for problems where a 4% 90% success rate is unacceptable, the extra compute pays for itself immediately. But if Tree of Thoughts feels like the ceiling of complexity, wait until you see what happens when you stop writing prompts entirely and let the AI optimize them for you. Retrieval augmented generation. Every technique we've covered so far has one thing in common. They all operate entirely inside the model's own head. Chain of thought, tree of thoughts, self-consistency, all of it relies on knowledge the model already has. And here's the problem with that. A model's knowledge is frozen the moment training ends. It doesn't know what happened yesterday. It doesn't have access to your company's internal documents. It can't check a fact against a live database. Every clever prompting trick in the world is useless if the model's information is stale or it simply never had the data you need in the first place. Retrieval augmented generation, or your RAG, breaks that boundary entirely. It connects the model to the outside world. Here's how it works. RAG is a two-part system. When your query comes in, a retriever performs semantic search over a vector index of documents, essentially a massive library of information stored as mathematical representations. It finds the most relevant passages to your question and pulls them out. Those passages then get fed directly into the model's context window alongside your original query. The language model generates its response condition on both your question and the retrieved material. It's not guessing from memory anymore. It's reading the answer from a source. The primary reliability argument for RAG is hallucination mitigation. When the model has to ground its response in actual retrieved documents, its ability to confidently fabricate information drops substantially. The response needs to align with what the retriever found. And because the knowledge base exists independently of the model, you can update it anytime. New research comes out, add it to the index. Company policy changes, swap the document. The model doesn't need retraining. It doesn't need fine-tuning. You just update the library it reads from. That operational advantage is massive at scale. Retraining a large language model costs millions. Updating a document index costs practically nothing. For any knowledge-intensive application, RAG is dramatically cheaper to maintain than a continuously fine-tuned model. But here's the thing, RAG is only as good as its retrieval. A poorly constructed index, a weak ranking function, or irrelevant document chunks will cap your output quality regardless of how powerful the underlying model is. The model can only work with what it's given. Custom prompt templates for RAG systems matter too, because they tune exactly how the model interprets and integrates the retrieved context. Get that template wrong, and the model might ignore the retrieved documents entirely, defaulting back to its parametric memory, which defeats the whole purpose. One more thing worth mentioning here, because it pairs perfectly with RAG and everything else we've covered. Self-refinement. This is the technique where a model generates an initial output, critiques its own work, and then produces an improved version based on that critique. Simple concept. The results are not simple. Iterative self-refinement loop produce approximately 20% absolute performance improvements across tasks, including code optimization, dialogue generation, and mathematical reasoning. Even GPT-4 improves substantially through self-refinement without any additional training. That's a striking number for a technique that literally just asks the model to try again and do better. But if you think connecting a model to external knowledge is powerful, wait until you see what happens when the model starts making its own decisions about how to act in the real world. Multi-agent systems. Every technique we've covered so far has one thing in common. You, a human, are telling one AI what to do. Multi-agent systems flip that entirely. Now you're designing networks of AI agents that instruct, coordinate, and correct each other. And the results are genuinely staggering. Here's how it works in practice. An orchestrator agent receives a complex query. Instead of trying to solve the whole thing alone, it decomposes that query into subtasks. Then it spawns specialized subagents, each one getting a detailed prompt specifying its exact objective, output format, tool access, and scope boundaries. Those subagents go to work independently, report back with their findings, and the orchestrator synthesizes everything into a final, comprehensive response. Sounds straightforward, but the prompt engineering at this level is qualitatively different from anything else we've discussed. The orchestrator's prompt doesn't just tell the lead agent what to do. It teaches the agent how to think about problems, how to decompose queries with enough specificity that subagents understand their roles without ambiguity, how to allocate effort proportionally so simple subtasks don't get the same resources as complex ones, how to prevent redundant investigation across agents so 3 different subagents aren't all researching the same thing. You're not writing a prompt anymore. You're writing an instruction manual for a project manager. Research from Anthropic identified 8 core lessons that make or break agent prompting at this level. First, you need accurate mental models of how agents actually behave under different prompts, which requires extensive simulation and observation. Second, orchestration prompts must teach lead agents to decompose queries with sufficient specificity. Third, explicit effort scaling guidance prevents agents from overinvesting in simple tasks or underinvesting in complex ones. Fourth, and this is where it gets interesting, the system must enable agents to improve their own prompts through failure analysis. When an agent fails, a high capability model can analyze that failure and propose better prompts for next time. Fifth, extended thinking mode, where models generate visible intermediate reasoning before producing outputs, dramatically improves planning quality. It essentially gives agents a scratch pad. Sixth, maximizing parallel tool execution across subagents. Seventh, building in verification steps so agents check their own work and catch errors before reporting back. And eighth, designing robust feedback loops between the orchestrator and subagents so instructions get refined in real time as the task evolves. That parallelization lesson is where the efficiency data gets hard to ignore. When orchestrators spawn multiple subagents in parallel and those subagents execute multiple tools concurrently, research shows 90% reductions in task completion time compared to sequential single agent approaches on equivalent work. 90%. That's not an incremental improvement. That's a fundamentally different speed of operation. But here's where this story takes its most interesting turn. Sitting naturally at this level of complexity is something called automatic prompt optimization. These are algorithms that use language models to generate, evaluate, and iteratively improve candidate prompts, treating prompt quality as a learnable optimization problem. The system proposes a prompt, tests it, identifies weaknesses through model-generated critiques, then uses those critiques as directional signals to edit and improve the prompt. Think of it like gradient descent, but with natural language instead of numbers, and the results are remarkable. Gradient-guided approaches using these model-generated critiques as optimization signals improve prompt performance by up to 31% over Monte Carlo search methods. More importantly, these systems consistently match or beat human-written prompts on the same tasks. Let that sink in for a second. This entire video has been about humans learning to communicate more effectively with AI. We started with zero-shot prompting, literally just asking a question and hoping for the best. We moved through few-shot examples, chain of thought reasoning, self-consistency, tree of thoughts exploration, retrieval, augmentation, and structured output control. Every technique was a human getting better at telling a machine what to do. And the endpoint of that complexity curve is systems that engineer their own prompts better than we can. The field began with people carefully choosing their words to coax better answers out of language models. The frontier is language models that design better instructions for themselves than any human prompt engineer could write. Every technique in this video still matters. They're the building blocks. But the ceiling of this discipline isn't a perfectly crafted human prompt. It's a system that makes human prompt crafting obsolete. That's either the most exciting or the most unsettling sentence in this entire video. Probably both. If you enjoyed this video and want to see more, click the video on the screen now.